Okay, so this week we're going to jump into the electric field. We sort of hinted at what that was last time. This time we're going to get into a bit more of the details. So as far as topics covered in regards to the electric field, we have various electric field models. We're going to talk about limiting cases, which will actually be really useful. The idea being, if we set up an electric field, we can sort of look at it in such a way we can make it look like a point charge. And if we can make it do that, then we know we've set up the electric field correctly. We're going to talk about multiple point charges. We're going to do a quick example, and then talk about the electric field of a dipole. So with electric field models, we sort of talked about the electric field of a point charge, which is simple. It just radiates out every direction. But of course, real world objects, they have a lot of electrons, like a whole bunch of electrons, like even in like a chair or your desk or the computer you're looking at. Lots of electrons, and they can be arranged in really weird ways. Just depending on what's going on. So it's a really complex thing to try and tackle with just like Coulomb's law, trying to add up billions and billions of individual interactions. So to do this more practically, what we can do is calculate the electric field of a complicated distribution of charge. And we can do that by just sort of making some simplified assumptions and simplified models of the electric field. So we have four basic electric field models that we'll look at. We have a point charge. So if you have a really tiny charged object and you're sort of far away from it, you can just say, oh, that's a point charge. We have an infinitely long charged wire. So obviously, with such a wire, there's no real infinitely long wire, but you can imagine this like perhaps you're an electrical engineer and you're working on the wiring in like a Boeing 737. So even though the wires aren't infinitely long, if you're standing close to a wire and you look both directions, but you're only interested in like one little section of it, you can say you can assume that it's an infinitely long wire. So this is an assumption, but it can be a helpful assumption. We can also talk about like an infinitely wide charged plane. Obviously, these don't really exist in the real world, but if you have, and we'll see this later, if you have like a charged plate that's maybe 3 inches by 3 inches, and all of your calculations have to deal with like being right on the surface, well, you can assume that it's pretty much uniform and evenly distributed, and you can sort of use this assumption that it's infinitely wide given your setup where you're really close to the surface. If you start backing up, then it gets more complicated. And then, of course, we can have a charged sphere, so essentially a point charge, but larger with a charge distributed around its surface. Okay. Now let's think about what's going on in some of these situations. We'll go with the infinitely long charged wire, or at least a really long charged wire. So suppose we have a group of charges acting on a single point charge. How can this be modeled? Okay, so I've only drawn 3 over here, but you can imagine we have these opposite charges. So this little negative charge here on the end wants to draw this positive charge toward it. They're opposite charges, but at the same time, in addition to F1 on 3, we also have F1 on the positive charge. We also have the force of F3 over here on the positive charge. So this negative charge over here wants to pull it in this direction. We also have this middle charge, F2, on the positive charge, which is trying to pull it straight down. And you see that if we drew all these in here, it's going to get really sloppy, right? But what we can do is we can actually add up those individual forces, just like Newton's second law. Sum of the forces equals F equals ma. So that means we would get an acceleration if this positive charge isn't nailed down to the floor or the wall here, then it would move for us in this situation. And that's due to the sum of the forces. So what we're going to do is essentially add up all these individual force vectors that I've drawn. So we've got the first three here that were originally in red. Then we keep going. Each negative charge will get its own term in here. That's why I've generalized it just with the I notation. And then, of course, we can abbreviate it with the summation notation. So we sum up all those individual forces, and that's the net force acting on this positive charge. Okay, well, we can also calculate the electric field at the location of this positive charge. So if we wanted E here, well, all we have to do is just divide out the value of our test charge. We know what our test charge is. It's that positive value because that's the location we're looking at. So we just divide out that positive charge, and then of course we can add up all these individual generated electric fields with each of those negative charges. Each negative charge along this wire is going to generate its own electric field, and then this positive charge is going to interact with all those electric fields. So the net electric field is the vector sum of the electric fields due to each charge. And you may remember this from last semester, but that is the principle of superposition, where you can add forces together sort of on top of each other, and they are summative. Okay, now I said we'd talk about limiting cases. So if we get really far away, any finite object appears to be a point charge, right? You can imagine if you had a little charged plate, I don't know, perhaps this book is a charged plate. If I put this 30 feet away from me, it's going to look smaller. I put it 60 feet away from me, it's going to look smaller. Until eventually, it's so small, I can actually just say, well, this is kind of like a point charge. And that's the idea here. If you get really far away from any finite object, this isn't true for like an infinitely long wire or sheet, but eventually you're going to be able to approximate it as a point charge. So this is a limiting case. And the beauty of these limiting cases allows us to check a solution by seeing if it has the expected behavior as we get really far away from it or really close to it. So if we do some math, which we're getting ready to do here shortly, if we calculate an electric field from a continuous charge distribution, and it's a finite object, we can sort of check our work by using limits to see what's going to happen if we get really far away. If it looks like a point charge, then we're probably correct. We can also use simpler expressions for electric fields at points very close or very far away from a charged object. Right? So not only can we check our work, but we sort of get the simplified model if we're going to look at electric fields from a distance. Okay, let's talk about this whole idea of multiple point charges just a little bit more before we do a problem here and actually calculate electric field of a continuous distribution, which I believe is in this video. It might be in the next one. So the vector sum of an electric field, of course, can be written as the sum of the x components, the sum of the y components, and the sum of the z components. So if you have, even like in our last example, if you had, I don't know, 100 separate charges and they were all acting together and their electric fields are superimposed, you would literally just have to take all the x components from all those electric fields, add those together, to get your net X electric field. Same thing with Y. And we won't really do it in this course, but just be aware, if you're doing 3 dimensions, you've got the Z direction as well. Now, once we get these net X, Y, and Z pieces, basically with all these electric fields interacting, we're going to have sort of a total net direction for each. So we can actually take all 3 of these and drop them in to I hat, J hat, K hat notation. And that's essentially just going to give us each component in a nice compact notation, which we've done this in previous lectures this semester, just dropping things in this particular notation. It just gives us those individual components for us. We can also write the net electric field as both a magnitude and a direction. And you've done this plenty of times in Physics 1, where perhaps you report a velocity at some angle above the horizontal. So this is also a magnitude and a direction. So we can do the same thing with an E field. So just to quickly go over sort of a problem-solving strategy. For now, in these first couple of problems, we're just going to model charged objects as point charges. And then we'll, of course, need to draw a picture for the any pictorial representation is going to be helpful. So we need to set up our coordinate system and show the locations of charges. Okay, sort of sounds like Physics 1 all over again. You pick your coordinate system that's going to help you. You label it, know where your charges are in this case. Now you need to identify the point P at which you want to calculate the electric field. Okay, that makes sense. If you're interested in electric field at some point, you can label it with P. Now you'll, if, let's see, let's say we have, perhaps 2 electrons down here and a proton, and perhaps we want to calculate the electric field from these 2 electrons here at point P where the proton is. Okay, well, I've identified my point. I could even throw in my coordinate system. Okay, so one of these is at the origin. One of these is over here on the x-axis. And it looks like this point where the proton is has a component in the x direction and a component in the y direction. So there's my point. I need to draw in, let's see. Need to draw in my field. So I've got an E field going this way and an E field going this way. So I've got my 2 electric field vectors drawn in there. Okay, so I've done that. Now in this case, this is a poorly drawn picture, so there may not be any symmetry to see if anything cancels out. But if we suppose that this is actually right in the middle, perhaps this distance is the same as this distance, so we make like a little equilateral triangle. If that's the case, then we know the x components would cancel out, so those are gone, because we would have nice symmetry down this problem. Okay, so we could do that. Now that we've went through this little fake example just to demonstrate and give a pictorial representation of these steps, now we can jump to the mathematics of this. Okay, so the physics is over. Now we're just looking at the mathematics. So for each charge, you would just determine its distance from P and the angle, right? Okay, so now you're just getting vector components. It's just vector components. Okay, and you just calculate the field strength of each of those charges electric field, and then write each of those in component form, right? So we did that here. We're going to write each of these in component form. Then you'll sum everything up. And then if you needed to determine the magnitude and direction of the final vector, not all individual ones or anything like that, but just the final vector, then you can do that depending on what the question's asking. And then of course at the very end you want to check that your results have the correct units, and it makes sense. You're not getting like an electric field that's larger than, some electric field in like a CAT scanner or something. And of course you want to make sure that it agrees with any known limiting cases. So this is the part where you sort of take a step back, increase your distance, and see if it starts looking like a point charge. All right. So let's talk through this one example here. So there are 3 equal point charges, all of charge Q, and they're located on the y-axis at 0, 0y, and then plus or minus some distance d. Okay, so we have those there. Here's my distance d on each one. Okay, so we got that set up. Now, what is the electric field at point P on the x-axis? So that's over here. All right, well, we can go through those previous steps. We have the pictorial representation. What's next? We need to identify P. We did that. Now we just need to draw the electric field of each charge at P. Okay? Well, we know that the electric field is going to be positive. It's coming away from the charges, both charges. Okay? So we have, we'll say Q1, we'll do an orange. So Q1's electric field is going to point down and to the right at point P. Remember, we're talking about the point here. Don't get confused by where the vector is pointing. Okay, and we also have this electric field from point or charge 3, which is going to point up. Remember, it does just radiate straight away. And then we also have, and I'm running out of colors, we also have this charge here, and it's nice and just right on the x-axis for us. And we know at point P, obviously it's coming out everywhere, but at least at point P, the electric field is going to run right along this x-axis. Okay, well, we drew the electric field of each charge at P, so we're here now at this step. Okay, the next thing we need to do is basically just use symmetry and see if any of these things will cancel out. Okay, so I've got that noted here. You'll see before completing any calculations, the situation can be greatly simplified. Okay, so first, let's consider the y component of the individual electric fields. Okay, well, obviously, there's no y component on this particular vector, right? It's all in the x direction. So we don't have to worry about E2 here, the electric field from the second charge. What we do need to worry about are these other two, Q1 and Q3 electric fields, because they actually have a vertical component. Okay, you'll notice that, let's see, what color am I using for Q1? Using orange. So you'll notice here that we do have a vertical component on E1, right? It's got some stuff in the X direction, some stuff in the Y direction. So we need to figure out what this vertical component is. Now we're given this angle here, theta. Now we can use our trig, the whole SOHCAHTOA thing, and we know that we need the opposite piece from this angle, okay? So opposite, we know the hypotenuse. The hypotenuse is just E1, okay? So that's going to be a, let's see, it's going to be the SO of SOHCAHTOA, so that's going to be a sine. So if we take the length, which we know is E1 of this vector, so the hypotenuse, and then we multiply by sine of theta, that's going to give us the y component, right? So now we have this y component here of this electric field E1. It's pointing in the negative y direction. Remember, negative y is down. It's pointing in the negative y direction, so we know we're going to need this negative sign here. Okay, so that one's taken care of. We need to do the same thing for the Q3 charge. So we've got this component here. Looks like it's going to be another sign because it's the opposite for across from this angle theta. Okay, so we just take that magnitude, E3, the electric field from the third charge. Okay, and then we multiply by sign to get its y component. Notice it is in the plus y direction. Now, because this problem is very symmetrical, like the charges are plus d and minus d away from the origin, you can sort of use some common sense to say, well, we've got, let me switch colors. We've got this positive piece pointing up from the third electric field. And if we subtract what's going negative, because remember, E1 is in the negative y direction, if we subtract that, because they're essentially the same value, just one's positive and one's negative, well, because of the symmetry, these have to be equal. So this is going to be 0. So essentially the y component of E1 is just as much negative as as E3 is positive. So they do cancel out. Okay, so we've got the X stuff taken care of for E net. So we could essentially write that E net Y doesn't matter because it's all symmetric. All we want to care about is just the X direction now. So let's do the same thing again. Okay, for the first electric field, I can't even remember what color I used. I used orange. Okay, so here, here's our orange E1. What I want now is how far over in the X direction it is, right? So I want this adjacent piece. So this is my X component that I'm interested in now. How much is in that X direction? Now I can figure that out pretty easily. That's the K of SOHCAHTOA, right? Hopefully you all are familiar with that. I used it a lot last semester, but that's basically your sine, cosine, and tangent functions. Then the last two letters tell you what the ratio is: opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So looks like we want this adjacent piece, so this is going to be K. So cosine is going to be opposite or adjacent over hypotenuse. Now we know what the hypotenuse is. The hypotenuse is just the full magnitude, the length of the hypotenuse, the electric field. Then we're going to multiply that by cosine of theta this time because we want the X component. Okay, and it is positive. It's pointing in the positive X direction. Totally makes sense. Now for this next one, Q3, which I did it in blue. Okay, here we go, Q3. Just in blue, same thing again. I have this angle theta. I'm looking for the X component, so I'll just multiply by cosine. So it's the full value of that hypotenuse, the full vector times cosine to get that X component. And again, lo and behold, because of the symmetry, these two components are in fact equal. Okay, so the X components are they have the same magnitude and the same direction. And that's going to make this pretty easy. So remember, we already showed right here, we already showed that the y component completely cancels out to 0. We just need to sum things in the X direction. So here's my net X direction values. Okay, so E net is just the X component of the first, second, and third electric fields. Now remember what all we showed here. We showed that this one and this one are the same value pointing in the same direction. So let's just call it double E1 since they are essentially identical and we're adding them together. So 2 times E1, let's see. This one's a bit of a loner, so it still comes along for the ride. Okay, so now we know exactly what we need to calculate. So, oops. So we have 2 times E1. Okay, now we said that E1 was just the magnitude of E1 times cosine theta, because we're just dealing with the x component. Okay, we can plug that in. We know how to calculate the magnetic field, right? So really this is just the full strength of E1, and then the cosine just comes along for the ride. So the cosine just comes along for the ride. So full strength, but then we're going to use cosine to just grab the x component. So this is for the 2E1 x component. Now we can jump down to the x component of E2. That one's easy. There is no y component at all. It is just full strength in the x direction. So this one is just the definition of the electric field, right? No extra things needed. Okay, well, we know what this is now. We know what this is. We can just literally add them together. Remember, it's a superposition of fields. All right, so I've got this term here. Notice I am still multiplying by 2 outside. Here's my 2E1. Now I just need to also bring down my x component of the second electric field. All right, now we have an expression for our electric field, but the first term on the right-hand side is not in terms of x. So here's the problem. The first term on the right-hand side. Okay, well, this is the right-hand side of my equation, and that first term has an r and a theta in it. Okay, it's not in terms of x. So we've got this r and we've got this theta. That's the problem, because we have the second term, which has x squared in the denominator. How can we rewrite this first term to actually get it in terms of x? So here's what we're after. We want to convert first this r to x. Now let's think about how we're going to do this. So we have, let's see, we have this distance over here. This is the r we're talking about, r1 squared. Well, because this is a right triangle, right, we can see that. We know the sides. We know one side is d. We know the other side is x. Why don't we just calculate the length of the hypotenuse? Because this is literally just the Pythagorean theorem. C equals the square root of a squared plus b squared. Well, let's just use that instead. So what we can do is we can replace r with the Pythagorean theorem, and that's going to actually give us an x here. So that took care of one term. Now the next question is, how can we deal with theta? Well, let's use some trigonometry again, okay? So we have cosine is just opposite over hypotenuse, right? Opposite over, no, sorry, adjacent is adjacent over hypotenuse. So cosine is adjacent over hypotenuse. Okay, well, if we look at this angle here, theta, our adjacent piece is just x right here. Okay, so here's our adjacent piece. And then the hypotenuse, which we just used, is r, but we can also rewrite it as the square root of x squared plus d squared, right? So that is now our hypotenuse. So it looks like we can rewrite cosine of theta as x over the square root of x squared plus d squared, okay? So here's our cosine theta term. We've literally just used trig on both of these to rewrite it and get an x in there. So I won't go through the whole exponent rules, but here's just a simple jump. All we're going to do is simplify, because you'll notice we have an x squared plus d squared in the denominator for both of these. We just need to fix those exponents, and we can collapse this. Okay, and then of course we're just going to multiply across in the numerator and just get qx on top. All right, so that was, remember, that was just this one term here in green. All of that work was just for this first term. So we wanted to simplify it, get it in terms of x. Now that we did that, we can plug it in, which we did here. The other component comes along for the ride. We didn't do anything to that, right? It was set, it was good to go. So we could just bring it down. And then just for good measure, you can pull out all the constants out front. So this statement right here is your net electric field at point P over here, right? So it looks like a pretty wild field. And that's just from 3-point charges set up on axes. But now let's talk about limiting cases. And this math it looks gross, and I apologize, but there is no better way to get it all on one slide. But let's talk about some limited cases. We have this system, right, which we just dealt with. We know what the electric field is now. So let's ask the question, what if we get really close to the system of charges? So essentially, what if we move our point in and get it so close to this middle charge? We just slide down on the x-axis. So what's that going to look like? So that means what we can do is we could take our net electric field and just take the limit of it. We're going to let x get really close to 0. Okay, so I'm going to take the limit, which means I'll take the limit of the terms inside. Of course, the coefficients out front just come along for the ride. Now, this function actually exists at 0, this first term. Okay, so this exists at 0. Okay, so that means if the function exists there, I can just plug in 0. Now look at what happens. If I plug in 0, I'm going to have a 0 in the numerator. So that term goes to 0. And all I'm left with is just sort of the limit of 1 over x squared. Now, of course, that blows up as you go to 0 because the plot of that looks like this. But what we can do, and this is not the best notation, but it's physics, it's not a hardcore math class. Essentially what we can do is say, well, we're getting really close, but we're not actually letting it blow up. So that's why I switched to this approximate sign, right? So it's going to look similar to this. Okay, we're not having to get into like a whole 0 in the denominator thing. But look at what that is. This is literally, we could rewrite it just a little bit differently here. Q over x squared. That looks just like a point charge. And that makes sense. If we get really close, right here, if we get really close to Q2, if we make x really small, pretty much that one charge is going to dominate the electric field. So it makes total sense that if we get really close, all we're going to see is essentially just 1 point charge. And that's exactly what our limiting case looks like. Now, what if we get really far away from the system? We can do that as well. Okay, so if we let x get really big, let's do this in a different color. Let's do green. So if we let x get really big, that means we're going to move way over here. So I'll relabel our plot here with a P way over here. If we let x get really big, we can run through the same mathematics. And essentially what's going to happen is we can, if x is so much bigger than d, we can sort of ignore this bottom term, right? So the x squared and the 3/2 powers sort of going to simplify since we got rid of that d squared. So it's just going to be an x cubed, but we have a 2x in the numerator. Okay, well, those x's can cancel. We don't need them. So here's what that first term simplifies to if x is gigantic. Okay, now notice we have a common denominator, right? We have an x squared and an x squared, which means we can just add the numerators together and look at what we get. Once everything's simplified, we get a 3q up here. So again, we can rewrite this a bit. 1 over 4 pi epsilon naught 3q over x squared. So this looks like a system of this whole system of charges, because we have three, right? We have three charges. If we zoom way out, it looks like one point charge with a charge of 3q. So that makes sense. If we take these three charges, we move them really far away from us, we can't even like see the distance between all three of them, but we have 3q's there, right? So this is just going to look like a single little point way off in the distance, but we preserve the individual charges. All three q's will add up. So this also makes sense. Being really far away and just seeing the total charge, but not being able to tell what shape it is. So here in the math, it looks like just a point charge. Okay. Now that we've done that for just point charges, let's actually talk about the electric field of a dipole. So if we have two equal but opposite charges separated by a small distance, that is an electric dipole. Okay, so they got to be equal and opposite, and of course a small distance, not just any two opposite charges as a dipole. They got to be somewhat close together and interacting. We also have a permanent dipole. So this is going to be like a water molecule where we have oppositely charged particles, and they maintain a small permanent separation. Right, so hence the name permanent. It's not going anywhere. It's not temporary. It's a dipole that's always there. And you can see in regards to a water molecule over here, this H2O, you'll get some a negative charge on one side and then positive charge on the other. So here's your two charges separated by a small distance, and that creates a permanent dipole. We can also create a dipole essentially by polarizing a neutral atom with an external field. So this is an induced dipole. So if we make one and it's temporary and we have to be acting on it for it to exist, that's where you get an induced dipole. If it exists naturally and is always there, that's a permanent dipole. So in this case, we could apply, let's do this. Let's change this to orange and say if we apply a strong electric field, the electrons in the electron cloud of an atom, they'll sort of be drawn down on this electric field. The force experienced by the positive part, it won't be repelled and follow along in the direction of the electric field. So that's actually going to separate charges a little bit, and that's an induced electric dipole. Okay, so here's the most succinct definition. An electric dipole is represented by two opposite charges separated by a small distance. Now we can ask the question, what is the electric field of a dipole at some point along its axis? Okay, so this will be along its axis this way. So at this point, there will be two superimposed E fields. Okay, so that makes sense. We're going to have one E field from the positive charge, and then we're going to have one E field from the negative charge. Now let's think about what direction these are going to be. So if we think about our positive charge first, the E field is going to be pointing up and it's going to run along the axis. Okay, so here's our electric field from the positive charge. Now the negative charge is going to have an electric field pointing toward it. Okay, so here's our negative charge. The electric field is going to be pointing down. Now the green one is bigger because it is closer to the source charge. Let's see. Let's do this. So that's an important to note. See, notice the distance here. Oh, that looks terrible. There we go. The distance here is shorter. That means the positive charge, the green, is going to be stronger. That's why this vector is longer. Okay, so that means since these vectors are two different lengths, there's going to be a net electric field at this point when we add them up. Okay, so we're going to get, and you can see it here barely, this purple vector, that's my net electric field. Okay, now we can do the same thing with this axis here. So what if we were on the plane of the dipole? And what you'll notice, I'll do this quickly, we get the vector here, this green vector from the positive charge. We get this electric field going toward the the electric field in the direction of the negative charge. Notice there's symmetry, right, between these two. So let me do this. There's symmetry, so everything cancels in the x, so there's no x component. Because how much ever the green's pulling to the right, the blue's going to pull to the left the same amount, which means along this axis here, you just have an electric field in the negative y direction from this dipole, and that's just on the plane. All right, so I'm going to try and do a quick explanation here of the electric field from the dipole. So I'll run through this quickly and show you the math. This is also in the textbook, so you'll be able to read it and follow along. All right. So essentially we have these two charges, 2-point charges that make up dipole. So we have our positive component, which is here. We have our negative component. We can add these two things up. So we have our negative component here. Okay. We know that the negative component is going to be negative because it's pointing in the negative y direction. Now we need to represent these distances not by s, or by s and not by just r, right? We can be more creative and it'll actually be more helpful. So what we can do is take these r's and we can represent them in a different way. So the distance from the charge to the point that we're interested in is really just y minus half of this distance s, because remember, s is the total distance. So we just want to subtract off half of that, and that's going to wind up giving us our distance from the charge to the point. We can do the same thing. We can just take our distance y for the negative charge, and then you just add this extra distance down here. See how it goes to the origin, which is y, and then we have to plus or add half of the s value here, or the s distance. Okay, so that's just some simple geometry. Now we can replace those r values for what we just determined. So here's my two replacements. Now the rest is just crazy algebra. There's no big deal here. So you can see that after replacing with these two binomials for r, all I need to do is just pull out my coefficients from each term. Right, so these are going to go. Now I have these two seemingly gross terms here. Now I can I will let you all do it, but basically all you need to do is you just have to get common denominators. Right, so all you have to do is just multiply each term by essentially the thing it's missing. And once you get your common denominator, you can add those two terms together, and that's essentially is what happened here. Now, if you notice in the denominator, and you won't have to do this on an exam or anything, this is just for your information. But if you notice in the denominator for this particular statement. If y is very large, so basically, if you're much further away from the dipole than the actual size of the dipole, which is usually the case. Dipoles are usually close together, and usually you're really far away. If that's the case, in this limiting case here, you'll see that the whole denominator actually just simplifies down to y to the fourth. Well, let's just rewrite that. So we can take our big, gross, nasty expression and simplify the denominator and say, well, the electric field of a dipole is approximately this statement right here, 2ys over y to the fourth. Okay, we can simplify a little bit more, cancel out those y's. Okay, and here's what we get. And it turns out, I wanted to breeze through that math really fast just to show you this one statement, which will come in a little handy in the problem set. But essentially, this value, the charge times distance, and this is a specific distance. This is essentially the size of the dipole. Or the charge separation in the dipole. So this value is often referred to as the dipole moment. Okay, so the direction of P identifies the orientation of the dipole. Okay, and then of course the magnitude determines the electric field strength. The SI units, as you can tell, are coulombs meters. So if we replace the QS for the dipole moment, this would be the electric field of a dipole. And of course, R is the distance measured from the center of the dipole to the point of interest. Okay, so we're changing our notation from that previous example by just a little bit. All right, so that I just wanted to show you and give you this equation for the electric field of a dipole. Feel free to go back, and I encourage it to go through the math and sort of fill in those steps along the way. And here, just to finish, we have the electric field lines from a dipole included here. And of course, don't forget that you do have this little weirdness right here along the plane where you get the E field pointing in the opposite direction along this plane perpendicular to a dipole, whereas the electric field elsewhere, that's not necessarily the case. All right, so with that, I'm going to stop. If you have any questions, let me know. Next video, we'll actually talk about how to start doing some calculus and integrating these crazy distributions to calculate the electric field of billions of charges inside of an object.